Hello. Today we will be discussing section 2.1 with the topics parallel and aligned. We'll talk about vectors, their magnitude, as well as vector arithmetic. So the concept of parallel versus aligned are ways that we can further describe rays and vectors. So imagine I have two parallel lines that do not coincide with each other. They are distinct parallel lines. If I have a vector or a ray on both of these lines, these two vectors would be considered parallel. This is parallel versus if I have a singular line and I have two vectors or rays that are on the same line, this is known as aligned. However, because they go in one direction, we could imagine a situation where we have two distinct lines. One ray is going one way, and the other ray is going the other direction. We call this opposite. And then we have another way that we could, the last kind of thing that we could see is if we have a ray and another ray traversing the same line but in opposite directions, we again would call this opposite. So putting these two notations together, we have opposite parallel, opposite aligned. So what these we can distinct them as directly. So now these not only are parallel, but they're directly paralleled, meaning that they're traveling in the same direction. Here this is aligned, but directly aligned because it's traveling in the same direction. Parallel opposite, or more accurately, opposite parallel, is how we would define this. And this is opposite aligned. So I referenced direction, but we now have to kind of define what direction means. We're only going to consider a two-dimensional plane. So we don't have to worry about a third dimension kind of like out of the board. We can just imagine a regular graph. And we can label north as, so this is north, and this is the positive y direction. We have east. This is the positive x direction. You have south. This is the negative y direction. And we have west. This is the negative x direction. So if I have a ray that's going to start from the origin and goes off like this, I'm going to denote it as the following. This ray is traveling north 45 degrees east. So whatever direction you have, I'm going to first describe whether it's traveling in the positive y or the positive x, or sorry, negative y. And then if it's positive x, I'm going to call that eastward. Negative x would be westward. Now, this is 45 degrees away from due north being exactly in the positive direction. Now, I wouldn't say that if I was traveling exactly in the positive x direction, I would not call this north 90 degrees east. No, that's not how you would call it. You would call it due east. And that is going exactly east, much like due west, due south, due north. Huh? So now if I had a vector, and a vector, we're going to define it in a second, but let's say I had a vector here, and this is 65 degrees. I'm going to label this point A. Okay, so if I can imagine that this vector marks a little triangle with a change in x, I'm going to denote as x, and the change of y, I'm going to denote as y. I can think of this as a negative, or let's call this A, let's call this B. I'm going to think of this as a negative A and a positive B because my A is represented as a positive number because it's represented as a distance, but it's in the negative direction. And here my B is a distance in the positive y direction because I went north. So I could label this point, this A, as negative AB. Okay. So with that in mind, let's talk about a vector. A vector is a line segment with orientation. So what do I mean by this? Well, if I have a vector and it's going from point 1 to point 2, if I just drew a line segment, I can't notify where did I start, where did I end. So I said I started at point 1 and I'm going point 2, so I'm going to put a little arrow. That's the mark. I went that way. And so I'm going to say point 1, point 2, and I'm going to put an arrow, and I'm going to say that that is equal to little v. Now, what does this mean? Well, I started at point 1. That's why I have this little, that's why I started my arrow here. This is the tail of the arrow. And then the head of the arrow is point 2. So I'm going from point 1 to point 2, and I'm denoting that as a vector v. Now, this vector v, how can I calculate it? Well, I can think of it as the change in x and the change of y. It's keeping track of both these things. So if I say that point 1 is x1, y1, and point 2 is x2, y2, I can relabel this vector as x1 or x2 minus x1, x, or and then y2 minus y1. So that denotes my change in x, my change in y. Now the order of this is important because if I were to flip this, I'd get a negative number. Okay, well, if I flip this, I get a negative number as well. So I basically can have a negative and a negative. So essentially I'm going, if I was to flip it, I would describe the vector going in the other direction, going from point 2 to point 1. So be wary of that. However, let's look at magnitude now. The magnitude of vector v is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. That might look strikingly familiar because it's the distance formula from a previous video. This is exactly that. We have a change in x, we have a change in y, and we're going to square it. So if it was negative, it's now positive. Add them together so we have positive term square root, and we're going to get a positive distance. So this is just distance. That's all it is. So you can think of the magnitude of a vector is just the distance that the vector goes. Notice that the magnitude from P1 to P2 and the magnitude from P2 to P1 are going to be exactly the same because we don't care whether it's positive or negative change. Okay? So we will denote an equivalent vector they must have the same magnitude and the same direction. So in a way, vectors, we don't really care where we start and end them. We care about once we define the starting point, we know the change that we do. This change in x, this change of y, could have been done to any such vector. So if I had another vector over here, and this magnitude is equal to this magnitude, we call those equivalent if the direction they're going is the same, meaning that they are parallel, but directly parallel. Okay? So with this, we could also extrapolate that the zero vector. So if I have u equaling 0, 0, I'm going to denote that as the zero vector. I don't really have a direction because I'm at the same point. I could be facing any direction. It doesn't matter. So the zero vectors are all equivalent. It doesn't matter what direction is because it kind of loses the point of it. Okay. So how do we do arithmetic with these things? Well, first we can find some properties. And we can say, all right, what if I have a real number t times my vector v? Well, I'm going to denote my vector v as a change in x, change in y. So I'm just going to write xy. So this equals t times the vector xy. And this works exactly how you would anticipate matrix scalar multiplication. And we get tx for the top entry times ty for the bottom entry. We can also do vector addition. So say I have x1, y1. I'm going to add that to x2, y2. Well, that is equal to x1 plus x2, y1 plus y2. And we can denote this guy as maybe like a v1 and this guy as like a v2. Okay, so in other words, we have v1 plus v2 is equal to that guy. All right, what other things do we have? Well, they're associative, commutative. We have an inverse, meaning, or an additive inverse, I should say, so negative of a vector. So negative u plus vector u is equal to the zero vector. We also have that 0 times any vector is equal to the zero vector, which makes sense because if I have some arbitrary x, y, 0 times x is 0, 0 times y is 0, and so we get the zero vector as defined on the right-hand side over there. Okay, well, any real number times the zero vector will get us the zero vector, and that makes intuitive sense. If we have 1 times a vector, we get that vector right back. And then the distributive properties also work. So if I have t plus s, and I'm going to have a u, so t plus s times u, that is equal to t vector u plus s vector u. This works the other way. If I have a t times a u, a vector u plus a vector v, we get t vector u plus t vector v. And we also have associativity with scalars. So if we have like an st times vector u, we can times vector u by either one of these first. What that means is we can have s times t times vector u, or we could view this as t times s times vector u. We can do either one of those operations first. So now we want to try to pull these concepts together, and we're going to have a word problem to showcase this. So consider 2 cars that start at the same location. So car A travels 3 miles north, 65 degrees west. Car B travels 2 miles south, 35 degrees west. How far apart are the cars? So like any word problem, let's try to draw a picture and understand what's going on. So by first making a graph, I'm going to call the origin O because that's where they originated. I can just declare that that's the starting spot. And now car A travels 3 miles, 65 degrees west from north. So about, there. So I'm going to label 65 degrees because this is the northbound direction. And I'm going to label this 3 miles. And so this is point A, which I'm going to label as x1. I already use x. Let's change up these variables. Let's do u1, v1. U being the change in x and v being the change in y. So now the other car went 2 miles in the south 35 degrees east direction. So maybe about there. So I'm going to label this as 35 degrees. And I'm going to label it as 2 miles. And point B, which I'm going to have equal to U2, V2. Again, U2 being the change in X and V2 being the change in Y, or that's how I can think of this as a vector. So essentially we have the point U1, V1 for A and the point U2, V2 for B. We want to know what this distance is here. So what is D? So in order to solve this, we're going to subtract these two vectors, and that will get us the resulting vector, and we can subtract them in any order, and that will just get us what the vector is from point A to B or from point B to A. So let's be consistent, and we want to find A, B, and we want to find the vector. So we're going to start at A and go to B. We can work this the other way around, but I'm just going to define this direction. So we're going to try and find this vector here. Okay, so how we do this is we have the OA, that's the vector from the origin to A, minus the vector from the origin to B. Okay. So we want to find their changes. So this would be equal to U1, V1 minus U2, V2, which then this minus I can think of as a -1 and throw it into the vector, and that results in U1 minus U2, V1 minus V2. And that equals our vector AB. But we want to find the distance of this. So we want to find the magnitude of this guy. Okay, so we're going to get here, but first let's try to figure out what this U1, U2 is. So let's look at the first one. We have this angle, and we have a triangle that can form from, I can think of this as V1 as the change of y and the change of x as U1. So if I was to gather the change in x, that's the opposite leg compared to a reference angle of 65 degrees. Well, I know the hypotenuse, that is 3, so I can say that sine of 65 degrees is equal to U1 over 3. Timesing by 3 each side, and I have 3 sine 65 degrees is equal to U1. Now, this is a representation of a triangle which we have positive lengths. Here's where I have to think of the direction and go, hey, this is in the negative direction because we're going westward. So I have to attach a negative here because I started at the origin and I went in the negative x direction because I went westward. Okay. So this is car A. So now the next part is trying to find our change in y. Well, now that's the adjacent leg, so we can put cosine of 65 degrees is equal to V1 divided by 3. So we have 3 cosine of 65 degrees is equal to V1. And now we think back to the direction and go, we went in the north direction because we started at the origin and went north. So this change is positive. So we have a positive result. We're good. We don't have to touch the sign. All right. What about car B? So let's first look at the change of u and see, okay, how far did we travel? And again, we're going to use sine. So we have sine of 35 degrees is equal to u2 divided by 2. Timesing 2 to both sides, and we get 2 sine of 35 degrees is equal to u2. And now we have to think, what's the direction? Well, we went westward again, so that's the negative x direction. We can now write cosine of 35 degrees equals V2 over 2. Again, I look at my reference angle of 35 degrees, and I see that the adjacent leg is my change of y, that's my V2, and my hypotenuse is only 2 miles. So that's why I have the 2 in the denominator. Times by 2 to both sides, and we get 2 cosine of 35 degrees is equal to V2. Again, what is the direction? Well, we went south. That is the negative y direction. So we have to include a negative because of how we constructed this. We constructed this in the form of a positive length triangle. So these would just give us a bunch of positive values. We have to introduce the negative. Later on, we can find ways to make it where we don't have to keep track of the negative, but for now, this is how we do it. Okay. So, what does this all mean? Well, I can now write my vector OA. I can write this in the form of my change in the x, which is u1. So that's negative sine of 65 degrees. And I'm going to times by 3. So sorry, negative 3 sine of 65 degrees. And then I have my change in, or my v1, which is 3 cosine of 65 degrees. And from the origin to B, my vector OB is here, my U2, which is negative 2 sine of 35 degrees. And then my V2 is -2 cosine of 35 degrees. Now we combine these two. So let's flip this. And when I look at my goal, I want the magnitude of AB. So first I need to get AB. So I have this here. I'm going to end up having my first vector, which is -3 sine of 65 degrees, 3 cosine of 65 degrees. And I'm going to subtract it from -2 sine of 35 degrees and -2 cosine of 35 degrees. So that results in the vector -3 sine of 65 degrees minus a -2. So I'm going to put +2 sine of 35 degrees. And then I have 3 cosine of 65 degrees minus a negative. So I have +2 cosine of 35 degrees. So this describes my vector going from A to B. We want the magnitude. So looking at the formula here, or remembering it's just distance, we're going to take the magnitude of AB is equal to square root, and we're going to have -3 sine of 65 degrees plus 2 sine of 35 degrees. And this whole quantity, we want to square it. So now we're going to add the other component, and we're going to have 3 cosine 65 degrees plus 2 cosine of 35 degrees. And that whole quantity, we want to square it. So it's just like that. And you might be asking, well, why isn't he rounding this? It's because if I round it now, if I rounded it here, I'm going to introduce some error. I round it here, I'm going to introduce some error. Adding them together, I'm going to have a little bit more error. Squaring it, I'm going to have a little bit more error. And eventually it's going to turn into a lot of error. But now plugging this all into the calculator at once, we can then get that this is about 3.304. Now, you might go through and you might attach miles on this and say, hey, that's my answer. And I'd say close, but a really, really good rule of thumb is real world question, real world answer. This doesn't tell me what you're talking about. So I implore you to add a sentence like the following. After the cars travel, they are about 3.3 miles apart. So, what did I do here? I gave it an answer that makes more intuitive sense. If I told you 3.304 miles, you're gonna go, okay, that's about 3.3 miles. Because 0.3 miles, you can visualize and you can think, okay, yeah, I know about how far that is. Versus 0.004 miles. What is that? How many feet is that? I don't know. It's not something that you think about. So that's why I would truncate it to having 3.3 miles. I also define that the cars traveled that far because that is what the question asked. An alternative answer would be the distance between the two cars is 3.3 miles. Now, either one of these would be, I would consider the most correct solution, but please, please, please put it into words. And to continue that practice, that will be your check on learning for this video. Please put the answer in your words, or you can copy it verbatim, either case, but say this answer in your own words. That'll be check on learning. Thank you for watching and have a great day.